Hi, this is Mathematics with Tom. I am Tom and welcome to this video. Today we're going to talk about, this is section 2.7 in the book by Gilbert Stray. And we're going to start today, we're going to talk about the transpose of a matrix. The transpose. So here's how this works. I think we're going to start by example and then we'll study the properties. So we'll start with just an example. Let A be a matrix of 1, 2, 3, 4, 5, 6. So we have, this would be notice this has 2 rows and it has 3 columns. So this is a 2 by 3 matrix. Now if I transpose it, I write it this way, A, and I use a capital T in my superscript, or as an exponent. That was an ugly looking T. A transpose, and what I do is I literally flip the matrix. So you could think of it as 2 ways. You can think of the row, column 1 becomes row 1, column 2, which is 2, 5, becomes row 2, or column 3, which is 3, 6, becomes row 3. Wow, that's a mouthful. That's A transpose. And so look at what happened. Not only did row 1 become, or column 1 become row 1, you could also look at this as row 1. Row 1 became column 1. And so that's really important. So the transpose makes, and I'm going to use some notation that will help us here. I'm going to say row makes row 1 into column 1, makes row 2 into column 2, dot, 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 or you could think of it as it makes column, that it makes column 1 into row 1, and it makes column 2 into row 2, and then as many rows or columns into rows as there are in the matrix. So that's what the transpose does. Now, I think the best way to understand the transpose is to start out by kind of playing around with the idea. So I like this. Let's take the columns of A, and let's let X be the column vector of 1, 2, 3. And so I should probably say let X equal that, and Y be the column vector 4, 5. Excuse me, 4, 5, 6. Now let's play with this. Right now, when we have 2 column vectors, all we can do, we can't multiply, but we can take the dot product of X and Y. And if we do that, that would be 1 times 4 plus a 2 times 5 plus a 3 times 6, that's 18, 28. So, or we could just write 32. So all we can do is we can take the dot product. But now, let's experiment. Suppose we write it this way. What if we try transposing one of these vectors? Let's transpose X. So X transpose. Well, just like what we said up above, look at what we said. It takes a row into a column, or it takes a column into a row. So with just a single column vector, it becomes, we'd say, a row vector. So now the row vector, X transpose, looks like this. 1, 2, 3. It's just a matrix with 1 row. Well, let's see now if we can do anything with these. But first, let's remember this. Notice that X transpose is a 1 by 3 matrix or vector. And let's come up here. Notice that y is still a 3 by 1. Now, if I want to work operations on these, I have to do that so that the matrix multiplication will work out. So notice this. I can have a 3 by 1 multiplied with a 1 by 3. We know that that would work. And I could switch that. Notice that I could also have a 1 by 3 being multiplied with a 3 by 1. Well, what orders are those? The 3 by 1, this is y. And the 1 by 3, that's x transpose. Oh, and those are being multiplied. And then if we look at the other case, a 1 by 3, that's x transpose. And then the 3 by 1 is y. And so let's try both of these and see what happens. Okay, so let's try the first one. Let's try y times x transposed. Now, we've actually seen this before. So y is 4, 5, 6. And x transpose, we know that this is 1, 2, 3. Now, when we multiply this is the first row, 4 times each column of x transpose. Well, that's going to give me 4 times 1, 4 times 2, 4 times 3 for 12. Notice that our result should be a 3 by 3 matrix. So then we're going to take 5, and we're going to make 5 times 1 for 5, 5 times 2, 5 times 3, and again the process repeats with 6, 12, and 18. Okay. Now let's try x transposed y. Well, x transposed is now 1, 2, 3 times y, which is 4, 5, 6. Now, when we try this, so notice what's going to happen. We're going to take row 1 with the column. Well, what is that? That's just going to be a 1 times 4, a 2 times a 5, plus a 3 times a 6. Well, wait a minute. We've already done that. That was the exact same result as x dotted with y. We saw this. This right here, let me use my highlighter, is, oops, undo that. Let me see. This is that right there. So x transpose y is the same as the dot product. And these patterns have names. This second one that we just did, this is called an inner product. This is called the inner product. And y times x transpose is called an outer product. And notice that the outer product produces a matrix. The inner product, I should write that. That looks like kind of a mess there. Let's put that over here. That looks better. So the outer product, oops, I need to put my y back together. Goodness, I made all sorts of problems by doing that. Now, so I have an outer product, I have an inner product. Let's take a look at, now what if I had another vector? What if x transposed was being multiplied by something even more? Like, so we still had y, so 4, 5, 6, but then maybe there's another vector. Maybe it was minus 1, 2, 1. Well, notice what this would be. This would be x transposed times 4, 5, 6. So notice, and again, this is going to be a 1 by 3 being multiplied by a 3 by 2. So I should end up with a new vector it's going to be a row vector, one row, but it'll have two elements. And the second element will be x transposed times minus 1, 2, 1. And so you can work those out. Well, we've already done, no, we haven't done x. Yes, we have x transpose 4, 5, 6. Well, we already said that was 32. And then x transpose times 1, negative 1, 2, 1. That's going to be a minus 1 plus 4. That's 3 plus another 3 for 6. I believe that's correct. Okay, so now we've seen how the transposes are working. So let's take a look at the properties of the transpose. So here we go. I'm going to scroll up. I think we can do this. So properties of the transpose. Okay, we're going to put to use what we've just learned. The first one is addition, and it says that if you have two matrices, A plus B, and you transpose them, it's the same as just taking an A transpose plus B transpose. And so if you wonder, say our matrices are just vectors. We could use our x and y. Say we have our vector x plus our vector y. And let's see if that's equal to x transpose plus y transpose. Well, the x, we said this is 1, 2, 3, plus our vector y, this is a 4, 5, 6. And first, if we added them, well, then we're going to get 5, 7, 9. And then if we transpose it, this would be the vector of 5, 7, 9. And if you try the other way, if you take x transpose, well, that's going to be 1, 2, 3 plus y transpose, that's 4, 5, 6. And you can see that if you add that up, 1 plus 4, there's your 5. 2 plus 5 is 7. And 6 plus 3, there's your 9. And so now you're just adding matrices. Now, there's this first one. The second one, this one gets a little bit more interesting. And that one says that if you have the product, some matrix A, and times some matrix B, and you transpose those, then that's going to be B transpose times A transpose. And I want to take a bit and develop this idea because we're going to need this later in this class. And for simplicity, we're going to let A and B be 3 by 3 matrices. Okay, just like our X was in R3. Now, let's see if we can develop this idea. Let's try this. So, let's just start with what we know. If we have the matrix equation AX equals B, and let's transpose it. So, I'm going to take AX and transpose that, and I'm going to transpose B. Well, B transpose, this is more easy to see in the sense that, like when we transposed X, all it did is become, the column vector became a row vector, B1, B2, and B3. So that's easier to see. But what does that tell us? This tells us, this implies then that AX transposed is also a row vector. Wow, how in the world is that possible? Well, let's take a look. If I was going to multiply A times X, Well, what that would mean is that I would take row, oh, yeah, I'm sorry, I had to think about that for a second. Let me go back. Okay, so this is going to be A times X. That means that I'm going to take row 1 of A, dotted with X. And then I'm going to take row 2 of A, and I'm going to dot it with X. And then I'll take row 3 of A and dot that with X. Okay. Now let's transpose it. What do we get? Well, this is going to be X, and I don't need to switch the, we'll just be right with what we've got. So we have, this is going to still be row 1 dotted with X, and it's going to be row 2 dotted with X, and it's going to be row 3 dotted with X. Now let's do something here. Notice that X is affecting row 1. It's also affecting row 2, and it's affecting row 3. So X is operating on every single part of each row. I'm going to just reorder this. The dot product doesn't care about the orders. It's the same as X dotted with row 1. It's X dotted with row 2, and it's also X dotted with row 3. Now, wait a minute. Let's return. Now, I'm going to scroll up here. Let's return to what we first discovered about the dot product. Let's go up here. Notice that we said that the dot product x of x and y is the same as a row vector. This is a row times a column vector. Well, what does that mean? That means that we need to apply that down here. So how do we do that? That tells me that this is really, well, X, this is X transposed, but row 1 is not a row 1 anymore. It has to be a column, so it has to have been transposed. So this is row 1 transposed. This is X transposed, not times the row anymore, but times the column vector. So we need to transpose it to flip it, to get it into a column. And then finally, X transposed times R3 transposed. Well, let's put this together. We're almost there. This is simply matrix multiplication. And notice that the X was applied to, worked on every single column. So I can write this as X transposed being multiplied by X transposed the row times the column. The column is R1 transposed. And this is then R2 transposed. And then row 3, which is now the third column, so it had to have been transposed as well. But wait a minute. What did I just do? When we said earlier, we said up here, what does the transpose do? It turns rows into columns or columns into rows. In this case, we've turned rows into columns, and there it is. This is X transpose times A transpose. The rows have now become columns. So, how do we show now our final steps as we're going to figure out that AB transposed is B transposed, A transpose. And now we're ready. So I'm going to come up here. And so let's take this. Say we have the matrix A. Say I have the matrix A times, we'll just use X, where X is, again, capital X. This is a 3 by 3 matrix. Well, what does this mean? This means A times the first column of X. It means A times the second column of X. And it means A times the third column of X. Well, now let's transpose all of this. Okay, well, if we're going to transpose that, then that means that means that each one of these columns now becomes a row. Well, when I transpose those, in order to make those a row, then that means that the row 1 becomes x1 transposed A transpose. That's what we just learned over here. And then that we have an x2 transposed A transposed. And we have x3 transposed A transposed. But what is that? That is, remember, x1 transpose is, these are rows. So these are just now rows of x transpose times A transpose. And that's how we get that for matrix multiplication. All right, our third property. You ready? Third property. So our third property says that A transposed, the inverse of it is equal to A inverse transposed. So let's see how in the world that's possible. Well, if you recall, we said earlier that if you have a matrix A times B, and that equals I, and if you have the matrix C times A, and that also equals I, that it means a few things. It means that B is equal to C is equal to A inverse. Okay, let's try this. Let's apply this. So suppose then we have the matrix A times A inverse. And we know, whoops, let me clean that up a little bit. So let's write this as I. I equals, well, I know that I is equal to A times A inverse. And now let's transpose both of these. Transpose both sides. Well, when you transpose I, that you get I. And if you're like, no, how's that? Well, think about it. If I is maybe a 3 by 3 of 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, if you're going to transpose that, well, then I transposed is just equal to row 1 becomes column 1. Wait a minute. Row 1 becomes column 1, but those are the same. Row 2 becomes column 2, but those are the same. And row 3 becomes column 3. Those are the same. And so we can say that I transposed is in fact equal to I. Okay. Now, that was kind of quick, but if you look at it, you'll see that it doesn't change. The zeros just get flipped over the diagonal. Now, let's continue with our proof, or what we're trying to understand. So let's apply, if I have the product of two matrices, transpose, well, we're going to use this property. We're going to use this property that we learned right here. So this becomes A inverse transposed times A transposed. Okay. And let's try this again. If I take I and I transpose it, I get I. But what happens though if I take A inverse times A and I transpose that? Well, then I'm going to get, if I switch the order, this is going to be A transposed times A inverse transposed. Well, wait a minute. These both equal I, so what we're going to do is, since both of this equation and this equation, they're equal by the i's, then we can set the right-hand sides equal to each other. So let's do that. So then what does this say? This says then that A inverse transposed, A transposed, is equal to A transposed, A inverse transpose. Now here's the big step. Here's the big step. Look at what I have. I have that A transpose is being multiplied by a matrix on the left. Okay, that's on this side. And on the right-hand side, I have that A transpose is being multiplied by a matrix on the left. And not only that, but they equal I. They equal I. Well, this means, this implies, then, this means that A inverse transposed, it also has to equal the A transposed, the inverse of that. It has to be that. And so that's how you can say that the A inverse transposed is equal to A transposed A inverse.